Good day, everyone. We are the Group 2, and our topic is all about the wave theory of light. In the late 17th century, scientists were stuck at a debate about the fundamental nature of light, whether light is a particle or a wave. In the previous discussion, we learned about Sir Isaac Newton's strong advocacy about the particle nature of light. Now, in this video, we will take a glimpse about how Christian Huygens sees light as a wave and how it stood the test of time, which made it the backbone of optics. Before we jump to the main discussion on how light is a wave, let us first get to know the person behind this perception, and it is none other than Christian Huygens. He was a Dutch physicist, mathematician, and astronomer who was born on April 14, 1629 in Hague, a city in Netherlands, and died on July 8, 1695 in the same place. In 1678, Huygens proposed that every point that a luminous disturbance meets turns into a source of a spherical wave itself. The sum of the secondary waves, which are the result of the disturbance, determines what form the new wave will take. This theory of light is known as the Huygens principle. Huygens principle, also known as Huygens Fresnel principle, is a method of analysis applied to wave propagation problems, both in far-field limit and near-field diffraction and reflection. It states that every point on a wavefront is in itself the source of spherical wavelets, which spread out in the forward direction at the speed of light. The sum of these spherical wavelets forms the wavefront. The envelope of the wavelets is a surface tangent to the wavelets that make up the new wavefront. The three-dimensional envelope of a point source will be spherical if the medium is homogeneous and has the same properties throughout, allowing light or sound to travel at the same speed regardless of its direction of propagation. Otherwise, as in the case of light with many crystals, the envelope will be ellipsoidal in shape. Plane wavefront is produced by an extended light source, which will have an unlimited number of point sources.
Huygens' theory wasn't able to explain the diffraction effects of light. Later, in 1803, Thomas Young's experiment on the interference of light demonstrated that the Huygens wave theory of light was accurate. Thomas Young performed an experiment that strongly inferred the wave-like nature of light and paved a way for a better understanding about the differences of particles and light. To better start the discussion about his experiment, let us get to know first the man behind one of the successes in the field of quantum physics. Thomas Young was a British polymath who made notable contributions to the field of vision, light, solid mechanics, energy, physiology, language, musical harmony, and Egyptology, and was born in 1773 in Milverton in southwest England into a large Quaker family. In 1801, Thomas Young presented a serious challenge to Newton's idea on the nature of light. He was a prodigy as a child, learning to read by age 2 and teaching himself Latin at age 6. In May of the same year, while pondering some of Newton's experiments, Young came up with the basic idea for the now famous double-slit experiment to demonstrate the interference of light waves. The demonstration would provide solid evidence that light was a wave and not a particle. The double-slit experiment. To start off, in a double-slit experiment, a beam of light is aimed at a barrier with two vertical slits. After the light passes through the slits, the resulting pattern is recorded on a photographic plate. When one slit is covered, a single line of light is displayed, aligned with whichever slit is opened. Intuitively, one might hypothesize that if both slits were open, the resulting pattern would display as two lines of light, aligned with the slits. What occurs in practice, however, is that light passing through the slits and displayed on the photographic plate is entirely separated into multiple lines of lightness and darkness in varying degrees. If the beam of photons is low enough to ensure that individual photons are hitting the plate, one might expect there to be no interference and a pattern of light would be two lines of light aligned with the slits. The result of the experiment, however, indicate the presence of interference. Somehow, the single particles are interfering with themselves. On the face of things, this might seem impossible. We expect that a single photon will go through one slit or the other and will end up in one of two possible light line areas: diffraction and interference. The phenomena of diffraction occurs for all waves. Diffraction describes the event of waves encountering an obstacle and the consequential bending around the object. Additionally, waves may interfere both constructively and destructively, resulting in different wave patterns. The most common example of diffraction occurs with water waves, which bend around a fixed object. Light bends similarly around the edge of an object. They visibly change direction or diffract as they pass through the opening. Interference is the phenomena of two waves meeting and adding together to form a resulting wave that is the sum of the heights of each wave where they meet. When two waves interfere to create a larger peak, it is referred to as constructive interference. When waves interfere to cancel each other out or create a resulting wave with a decrease in height, it is referred to as destructive interference. The lower graphic shows the resulting waveform for two waves in phase and out of phase. The in-phase waves are interfering constructively, while the out-of-phase waves are interfering destructively.
That's it for our discussion. Thank you for listening.